Any questions on the individual gas laws or the combined gas law? Do we want to go over any examples on the worksheet? No? Okay. Let's talk about the ideal gas law. You want to review it?
Sure, we could really quickly, if that's all right.
Okay. So the combined gas law is P1 V1 over T1 equals P2 V2 over T2. Yeah. This is just, yeah, we'll do an example. Okay, this is the combined gas law. And remember, if you know this, you know the individual gas laws as well, right? If the temperature is constant, then we got that. We just erase temperature. Because if it's constant, then it doesn't really change, right? That doesn't change the value. If you divide both sides by 10, it's still going to be the same, right? And same thing if pressure is constant. Now you have that individual gas law. Or if volume is constant, we have that gas law. Okay? So do you want to do one with this? Do you have a question? No? Do we want to do an example with this one or just an individual one? Or should I just pick a random example and you guys decide what equation you use? Yeah? All right. Okay, a tank has a volume of 7.5 liters. That's how big the tank is. And it has a pressure of, let's say, 1,120 millimeters of mercury. And then later, pressure is increased, or let's say pressure is decreased. Might have to change something, but that's okay. Pressure is decreased to 960 millimeters of mercury. Let's say this is a balloon. Or something that can change volume. We want to know what is the new volume. Hello. Okay, so what's our first step? Yeah, we'll start with what you know, but first of all, we have to know what we know, right? So what do we know?
The volume is 7.5 liters. V1 is
Oh, so we're done, because it's asking for a volume, right? Oh, so V1 you say? Okay, that's our initial case. V1 is 7.5 liters. What else?
P1 is 1120 millimeters.
1120 millimeters of mercury. Okay, what else do we know? P2 is 960 millimeters of mercury. And what are we looking for? Oh, that's weird. All right, can we use this equation right here? Why not?
You have to use the, P1 times V1 equals P2 times V2.
Or we can just get rid of this one, right? Yeah. Or we could say that's what, 1? Or if we say it's 10 or 139, would it still work? Yeah, just multiply 139 to both sides and it goes away, right? We don't know what the temperature is here, it didn't tell us. But it's the same, since it didn't tell us, yeah, we don't need that one. So P1 V1 equals P2 V2. Okay, so we know what we know what we're looking for, and we have a method that we can use to solve this. That's the whole problem solving strategy. Now we just use it. How do you want to do it? Do you want to plug the numbers in and solve, or do you want to solve and then plug the numbers in? I'm hearing solve then plug the numbers in by one person.
I concur.
Okay. So we're going to solve for V2. How do we do that?
Divide both sides by
Divide P2 to both sides. And then plug our values in. P1 is 1120. Do we worry about putting our units? Yes. Because if by chance they're not the same, they won't cancel, and that'll tell us, I gotta do this, right? But if you just plug the numbers in and you're not paying attention with the units, you might have to convert it and you're not seeing it. Multiply V1, which is 7.5 liters, divide P2, which is 960 millimeters of mercury. What goes away? Millimeters of mercury. That means our answer is going to be measured in liters. If it tells us to put it in milliliters, then we got to convert, right? We good? So what do we get?
8.75.
And does that answer make sense? We lowered the pressure, so our volume should do what? Go up? Because they are inversely related. You with me? If we increase the pressure, let's see, if we increase the volume without change, then what happens to the pressure? It goes down. All right, makes sense to everybody? Do you want to try any with Avogadro's law? Okay. Let's say we have 3 grams of hydrogen gas at STP. We want to know how many liters of oxygen gas do we have in this reaction. So this is an applied problem. So it's like, a little bit more information, but we do it exactly the same way. What do we know? What are we looking for? How are we going to get there? What method are we going to use? So what do we do? What do we know? 3 grams of hydrogen. Is that all we know? Oh, STP. What does that tell us? 1 mole of any gas equals 22.4 liters of that gas. You with me? Okay. We also know what we're looking for. Liters of oxygen gas, a different substance. So what does that tell us we have to do? Stoichiometry. Anytime we're going from one substance to another, we have to have a balanced equation, and we got to use that mole to mole conversion eventually, right? So let's balance this. Does that make sense to everybody? Okay. Anytime you're going from one substance to another, we have to use stoichiometry. What goes in front of H2? What goes in front of O2? What goes in front of H2O? Okay. So, where do we start? Yeah, what do we know? 3 grams of hydrogen gas. We convert this into what? Yeah, we eventually have to get to moles of something else anyway, so we gotta always go to moles if we use stoichiometry. Okay, so what goes on bottom? How many grams? 1 or 2? Yeah, because the molar mass of H2 is 1.008 times 2, right? 2.016 grams of H2 to how many moles? 1 mole. That's just the molar mass of H2. Are y'all with me? Okay, we're not at liters of oxygen yet, so we keep going. What goes on bottom? 2 moles of H2, good. Any questions on that step? To what goes on top? 1 mole of O2, because there's a 1 right there. Okay, moles of H2 go away. We're getting closer, but we're not there yet, so we keep going. What goes on bottom? 1 mole of O2. Can we go straight from moles to liters? Yes. Since it's at STP, we know this value, right? 22.4 liters of O2. We're at liters of O2, that's what we're looking for. Tells us we're done converting. Now we just multiply and divide. What? That's a 4. Sorry. Need to write my 4s like this, but then it could look like a 7. I don't know. I just need to write better, don't I? 16.67, or just round to 7 liters of O2. Or we could just round to 17, right? Whatever. Good? Any other questions before we move on? We get a stoichiometry yet? Okay. Not too bad if you just step back and think about it. Or not think about it, just, I don't know. But, yeah, not too bad. Sometimes we make it out to be harder than it really is. Okay, so just realize it's just a conversion. All right, let's talk about ideal gases. So why do we call it ideal? It's in the case of, no, not necessarily. It's in the case that there's, everything goes perfectly. So the ideal gas law is basically for prediction only, right? Same thing with theoretical yield. It's prediction. The stoichiometry is prediction only, but it's pretty close. And if we do well if we measure well in our lab, our experiment, we're going to get really close to that. Okay. So this formula puts all four of the individual gas laws together. So we have the P1 V1 over T1 equals P, well, we just say it's constant, right? Can we just say it's constant? That's kind of how we derived it, right? But we also have, well, we had volume is proportional to the number of moles. So if we divide the number of moles and put a K right there, then we should get N1 right there, shouldn't we? Because that's also a constant. You understand that? Now let's figure out what this constant is, okay? The constant we're going to call R, just to kind of, it's not our little K constant anymore. It's R. And for certain units of pressure, volume, temperature, and moles, or the amount of substance, it's going to be 0.0821. And again, you have to use ATM for pressure. You got to use liters for volume, moles for moles, obviously, and Kelvin for temperature. If you don't have these units, we have to use a different number. Do you want to learn a whole bunch of different numbers? Yeah. So we just got to make sure and convert our units into these four units if we use this ideal gas law constant. Okay? Does that make sense? So that means PV over NT is equal to R. That looks a little bit clunky. Let's simplify by, we don't like fractions, right? Multiply both sides by NT. And then we'll just rearrange. PV equals nRT. Pervert, don't be a pervert. Okay, so that's the ideal gas law. And this is on your reference sheet. So is this value with the units. You could just look at your reference sheet and they're there. You don't have to write this on your little card, okay? Now, is this equation on your reference sheet? Is this equation on your reference sheet? They're not. But this one is. PV equals nRT. Let's divide T to both sides. Uh-oh. So PV over T equals NR. Well, if the amount of substance is the same, if we're just dealing with one amount of substance, and this is a constant, that means this whole thing is a constant, right? There it is. That's a constant. P1 V1 over T1 equals P2 V2 over T2. And just like we showed before, if temperature is a constant, then we have that one. If volume is a constant, we have that one, and so on. So really from here, from this equation that we have on our reference sheet, we can come up with all of the individual gas laws. Or if you don't want to have to worry about it, you have a little 3x5 card, you can put whatever you want on it, right? Your call. Make sense? All right, so let's do an example using the ideal gas law. So if we have 3.5 moles of O2 gas with a volume of 27.0 liters at 1.6 ATM, what is the temperature? So on the exam, it's not going to tell you what equation to use. So how do we know not to use one of the individual gas laws or the combined gas law? How do we know not to use that?
Because it gives us moles.
It does give us moles.
Cause it gives us moles, liters,
ATM.
and
It,
ATM,
good,
and temperature.
good, but one key thing that, to help us to know we use the ideal gas law here and not the other laws, is that we don't have an initial case and a final case. We just have one case. So we're gonna use the ideal gas law. Make sense? Okay? So let's write down what we know. That is
3.5
N
liters.
equals 3.5 moles. Okay? What's that? What is it? Volume equals 27 liters. What's this? Pressure equals 1.6 ATM. And we're looking for temperature. Do we need to know anything else to use this formula? R, and we do know that, right? And we know R is 0.0821 what? ATM liters per mole Kelvin. Okay, after you do this and do this and do this, you'll know just to remember to make sure you have the right units. And if you want to just do that first thing, okay, do we have ATM? Yes, we do. Do we have liters? Yes, we do. Do we have moles? Yes, we do. That means our answer is going to be in Kelvin. If it asks for the temperature in degrees Celsius, then when we're done, we have to convert it to degrees Celsius, which is the most time we got to know degrees Celsius because who understands Kelvin? Yeah, it feels like 273 degrees or Kelvin in here, right? We don't do that. We don't know. I mean, we know a little bit more now than we did before, but still, it's not like, yeah, let's know what it is. Probably for us, we have to know what it is in Fahrenheit, right? Because even degrees Celsius, like, yeah, I don't know that. I don't know. But, right? Am I wrong? Okay. All right, since we have it there, if we have all the units, they're matching, then we don't have to worry about the units. But I like to do it anyway just to make sure, because sometimes we get going fast, right? It's like, oh, hurry up and do this. Always use dimensional analysis. That's my suggestion to you. You can do whatever you'd like, okay? So PV equals nRT, and we're gonna solve for what? T, so what do? Divide both sides by nR. So we can plug our values in. We good? So pressure is 1.6 ATM. Volume is 27 liters. Number of moles is 3.5 moles. And R is 0.0821 ATM liter per mole Kelvin. Whoops. So what cancels? ATM cancels, liters cancels, moles cancels, but we have Kelvin on the bottom of the bottom. That means it's going to be on top, right? You with me? Okay. So now we just plug our numbers in and we get 150.3 Kelvin. Good? So we just added a few more things. But in a way, I think it's easier than the other gas laws, right?
ATM liter.
Maybe, because you don't have to worry about which one is V1, P1, all that stuff, right? But either way. Questions on this? Yeah, Chad. So the best way I can answer that is we have this right here. This is y equals mx plus b, right? Well, let's say b was 0. Then we have y equals mx, right? How is y related to x? Directly related, right? But it depends on the slope. So you're wondering, okay, that's what the constant is. This stays constant, right? The constant in this equation is the slope. So what does it mean in this one? Is that what you're asking?
Yeah.
Okay. It means the amount of pressure times volume divided by moles per temperature.
And for your ideal situation, it's always 0.0821.
If we use these units. If we use different units, it could be a different number,
Yeah.
right? And so, what does that mean? I don't know, but if we're using a real equation, I shouldn't say real equation, like if we say this is our position or distance, and this is our time, and we have an equation like this, then distance is equal to some constant k times t. Well, what does that constant k mean in this case? What does the slope mean? What is it?
Speed.
The speed. In this case, it's the speed. How do we know? Because it's rise over run, meters over seconds, times seconds is going to give us meters, right? And we know meters per second is a speed, but here, do we know what that is? Not really. But it's still our constant. So I can't tell you better than that.
Okay.
Yeah, I don't know, maybe. We good? If I scared you with y equals mx plus b, don't worry. Okay. Oh, this is mathy. Don't bring math. Okay. You want to try another one? Yeah.
Quickly, can we go back up to the previous section there quickly? So, since r has a fraction that's sort of associated with the number, when you have it in the denominator like that, how is it that you're still able to cancel even if they're both like on the same
Okay.
side of the fraction?
So you're talking about right here?
Yeah.
Okay. So we have, I'm going to rewrite this, 1.6 ATM times 27 liters over 3.5 moles, 0.0821 ATM liters per mole Kelvin. So you're wondering how I can cancel those?
Yeah, or moles for that matter.
Okay. So if let's how do I? So this right here is on the numerator of the denominator, right? So it's like we have, let me rewrite it another way. 1.6 ATM times 27 liters divided by 3.5 moles, 0.821 ATM liters.
0.0821.
Yeah, 0, sorry. And then 1 over moles and 1 over Kelvin. Do you see if we just focus on this part right here, we get that? No? So if we're just looking at this, we can multiply these fractions. and we get 1 over mole times Kelvin, right? You with me? These two right here. Okay, and then if we multiply this by this, then we're going to get 0.0821 ATM liters over mole Kelvin. Do you get that? So forget about this right now. Just looking at this right here. No? Do we see that or no? Okay. So here we can cancel, this is ATM and ATM cancel, because ATM's on the bottom, right? Liters, same thing. And now if we're just looking at this bottom part, this mole's on top and that mole's on bottom. You with me? Because we're just looking at the denominator by itself. And then what we have left is some number over 1 over Kelvin. Well, how do you divide fractions? You flip and multiply. Do you understand why we can flip and multiply? Anybody want an explanation?
Sure.
Okay. What can we multiply this and without changing the value? 1, right? Can that 1 look like this? K over 1 over K over 1. Anything divided by itself is 1, right? When we choose that one so that it cancels those, we just flipped it and multiplied by it, right? That's why we can. And so our answer is going to be in Kelvin, even though our Kelvin is on the bottom here. It's on the bottom of the fraction, on the bottom of the denominator, so we flip and multiply it. Was that your question?
That was my question.
Oh, yeah, your question.
But yeah,
Okay.
I'd say that makes more sense. I think we have similar voices, but.
Okay, yeah, because I thought you asked me the whole time. Sorry.
Thank you for that.
Yep. All right. Oh, let's see. Do you want another example? How you feeling? Yeah? Okay, let's do it. Okay, if we have a 500 milliliter canister, what's that? Volume equals 500 milliliter. So this is how I go about solving the problems. I actually write this down as I read the problem. Yeah? So this 500 milliliter canister, which can withstand up to 15 ATM. What's that? Pressure of 15 ATM. So that's the max pressure safely, is what it says. How much gas can it safely carry at room temperature, which is 25 degrees Celsius? So what's that? Temperature is 25 degrees Celsius, right? So we want to know how much gas. How much gas can safely be in this canister? Okay, so like a paint can or something, or aerosol can maybe. All right. So what are we looking for? N. The number of moles is the amount of gas, right? So we are looking for moles. So N equals question mark. Good? Unless it tells us in grams, then we'd have to convert moles to grams when we're done, right? But at this point, we're looking for the number of moles. If it asks for grams, we'd still have to find number of moles first, and then convert moles to grams using the molar mass. You with me? Okay. So PV equals nRT. We have everything but the number of moles, so we can solve for it. So divide RT to both sides. And we plug our values in. Should we plug our values in first? Or should we make sure we're in the right units? Okay. According to R, has to be 0.0821 ATM liter per mole Kelvin. So always check that until you get good at this, right? So how many liters is 500 milliliters? 0.5. And if you can't do that in your head, guys, just start like this, right? No problem. Do what you got to do. And 25 degrees Celsius is 298.15 Kelvin. Okay. Now everything's in the right units. Now we can use our equation. So we got PV, pressure is 15 ATM. Volume is 0.5 liters. R is 0.0821 ATM liters per mole Kelvin. And our temperature is 298.15 Kelvin. Make sure everything cancels out except for what we're looking for. Moles are on the bottom of the bottom, so it's going to be on the top when we're done. So good, that's going to give us the number of moles, and we get 0.306 moles. Questions? No? Pretty straightforward. So you get that formula, you just make sure they're in the right units. That's the key. Okay? You ready to try an applied problem? One that uses everything we've learned so far? Well, not everything, but a lot of the stuff. Or do we have any questions on this? All right. So let's say we have, so this is another example. We have sodium plus water gives us sodium hydroxide and hydrogen gas. If 3.5 grams of sodium react with plenty of water, how many liters of hydrogen gas will be collected at a temperature of 25.3 degrees Celsius and a pressure of 1.05 ATM?
3.5 gas.
What? 3.5 grams of sodium.
Temperature.
So we know. So this is just like we did outside, right? We threw the sodium in water. The temperature outside is 25.3 degrees Celsius, and the pressure outside is 1.05 ATM. We want to know what the volume in liters of hydrogen gas are produced in this reaction. So what do we do first?
Convert grams to moles.
Yeah, if we're going to use, we have temperature, pressure, we just need the number of moles, we can use,
Grams to mole.
yeah, so we go 3.5 grams of sodium to moles using the molar mass of sodium, 22.99 grams of sodium to 1 mole. Okay, so that's going to give us N. N equals what? 0.076 moles?
I got
No. Sorry.
1.15.
Nope. My bad. 0.152
Yeah.
moles of sodium. Okay, great.
1.14.
Now what? Can I use the ideal gas law yet? Why not?
Convert.
We need liters of hydrogen gas. We got to get to hydrogen gas first, right? Yeah. Great. So we have 0.152 moles of sodium, and we're going to convert moles of sodium into moles of hydrogen. What's the ratio? Is it 1 to 1?
It's not balanced.
Oh, yeah, we must have a balanced equation, right? So there's going to be a 2 right there, and that gives a 2 right there and a 2 right there, right? So now the ratio is 2 to 1. 2 goes where? On top or bottom? On the bottom. Y'all following me? Questions? 2 moles of sodium to 1 mole of hydrogen gas. And so I just divide that by 2 and I get 0.076 moles of hydrogen gas. So really that's my N, right? You follow that? So don't just find a number of moles and just plug it in. You got to be in the substance, in the right substance that you're dealing with. Sodium is not a gas. We should never use solids or liquids. You never use the ideal gas law for solids or liquids. Okay? So now we can rewrite this so that I'm kind of getting up here a little bit. So we have N equals 0.076 moles. Temperature is 25.3 degrees Celsius, which is equal to what? 298.45 Kelvin. Okay. Change it while we're at it. And the pressure is 1.05 atm. And so we're looking for the volume in liters, so we're good. Does that make sense, or did I go too fast? Slow down. So if we start back here, we want to know liters of hydrogen gas. So we got to have moles of hydrogen gas. Do we have to have temperature and pressure of hydrogen gas? No, that's the conditions for all of this stuff, right? But since we're looking for volume of hydrogen gas, we have to have moles of hydrogen gas. Does that make sense to everybody? Okay. And that's why we convert grams to moles and then moles to moles of hydrogen. Once we have the moles, now we can use PV equals nRT and solve for V by dividing P to both sides. Good? So we get V is equal to 0.076 moles times R is 0.0821 atm liters per mole Kelvin. And don't try to memorize that right now, guys. Use your reference sheet. And so that you make sure you get them in the right order, okay? Multiply the temperature, which is 298.45 Kelvin, divided by the pressure, which is 1.05 atm. Moles cancel with moles, Kelvin with Kelvin, atm with atm, and we're left with liters. And that's what we're looking for. So now we just have to multiply and divide, and we get 1.77 liters of hydrogen gas. How are you feeling? So a lot of equations in this unit. We're doing okay mathematically? Okay, yeah, we have one more topic to cover, and then we're done with this unit, or this chapter, and then we'll be done for today. Is that okay with everybody? Let's see if we can finish before break. If not, no big deal. Okay?
So if R is on top, we multiply, but if it's on bottom, we have to divide when you do it all the time?
That's right. Yep. If anything's on bottom, you divide by. If anything's on top, yep. So depending on what you're looking for.
Only we need to find the volume.
What?
Everything. Yeah, everything, but only we need to find the volume.
Yeah. And that's what we're looking for, so that tells us we're doing it right. We have the right unit. We double checked what the question was. We're good.
We don't have the right school background.
We don't have to what?
We don't have the right school background.
I didn't hear you, sorry.
I will tell you.
Okay, any questions on the ideal gas law? Or any of the gas laws? Okay, there's one more law, and this is the law of partial pressures. What if we have a mixture of gases?
We can separate it.
We got a mixture of gases that we breathe, right? Mostly what?
Oxygen.
Nitrogen. 78% nitrogen, 21%, you don't have to know this, nitrogen, a little bit of carbon dioxide, a little bit of water, a little bit of argon, whatever, right? So we got a bunch of gases in the atmosphere right now. So if we're talking about the pressure, the atmospheric pressure, well, what's the pressure that nitrogen, what's the partial pressure of nitrogen? Okay. So if we have the total pressure of our atmosphere,
What is the
I'm just going to say T, PT, total pressure. That's going to equal the pressure of gas A plus the pressure of gas B plus the pressure of gas C plus however many gases you have. Does that make sense in your mind? Pretty straightforward. Okay. So if we have the pressure of this room, for example, we have a certain number of moles too, don't we? Can we say we have a total number of moles? What's that going to equal? Yeah, the number of moles of substance A plus the number of moles of substance B plus the number of moles of substance C plus so on. Pretty straightforward? Okay. What's the relationship between pressure and the number of moles? Let's say we get a balloon and we want to blow more in it. No, not a balloon. That's not good because the volume changes. Let's say we get a balloon that the volume doesn't change. And we add more air into it. What happens to the pressure if the volume doesn't change? It goes up, right? So pressure is directly related to the number of moles. That good? So we can say the total pressure is related to the total number of moles. Can we also say the partial pressure of A is proportional to the number of moles of A? And B and C and so on, right? Okay. Well, if we take this, let's just go for general. Can we change this to an equation? We got P equals K times N, right? We've done this like 4 times already. Divide N to both sides. And that means our pressure divided by the number of moles is going to be constant. You with me? So can we say the total pressure over the total number of moles is equal to the partial pressure of substance A over the total number, or the number of moles of A? Can we say that? Because it's always constant, right? All right, so let's, I'm going to rearrange it just a little bit mathematically. Multiply both sides by number of moles of A. And divide both sides by total pressure. Do you follow what I did mathematically? We good? So then I rewrite this equation as the number of moles of one substance in comparison, in ratio to the total number of moles, is equal to the partial pressure of that substance over the total pressure. And we call this the mole fraction. Big deal, right? So this, is this on your reference sheet?
No.
So you need to know this. Okay? So the ratio of moles is equal to the ratio of pressure. And what's on bottom? The total. Always the total. Okay? Can we also say NB over, NT? And we can also say PB over PT, right, and so on. Okay. So now we can determine what the partial pressure is of each gas in a mixture of gases. You ready for an example? So it's just another formula. It looks not any more complex than any of the other equations we did. It's just a different one. So let's do an example. Okay, let's say we have let's say in this room, and these are not exact numbers for this room, but let's just say in this room, it's airtight. We're in a not a vacuum, but airtight room. We can't lose any air. We can't get any more. And we have 2.78 moles of nitrogen gas in here. We have 0.75 moles of oxygen gas. And we have 0.03 moles of argon, for example. I know we have carbon dioxide and water, but that's okay. We'll just keep it simple. Okay? So let's say we measure the pressure in here. We get a barometer. We measure the pressure to be 0.987 atm. I want to know what the partial pressure is of each one of these gases. So what's the pressure of N2? What's the pressure of O2? And what's the pressure of argon? Any questions on what I'm asking?
So P total is the 0.97.
That's right. Good. That's the pressure of this room. Yep.
What is the T, the PT?
Yep. The total pressure. We good? So we want to find all of these. Let's just do one at a time. We're going to use this formula right here. So let's find partial pressure of nitrogen over the total pressure is equal to what? The number of moles of nitrogen over the total number of moles. Are we good? Okay. We're looking for that. That's our question. We know this. It's right here. Do we know that? It's right here. Do we know this? We can find it pretty easily, right? What's the total number of moles? You add those together, right? And what is it? 3.56 moles. Does that make sense to everybody? Okay. So let's solve for that guy right there by multiplying total pressure to both sides.
Do we have the NT?
What? What's your question?
The pressure of NT equal
N2.
N2 on the top 3.56.
We don't know what that is. We're looking for that. That's our question.
No,
What's the partial pressure of N2?
NT, but you said 3.56.
Oh, NT. Yeah. Do you know where we got that? We add this number of moles plus this number of moles plus this number of moles. We add, so NT, just like we showed up here, the total number of moles is the sum of the number of moles of each gas. Does that make sense? Mishka, did you have a question? No, maybe it was Rebecca. Somebody had their hand up. Oh, Mariana. We could. We definitely could. But then the NT would be over here. Then we'd have to divide by it to get this by itself anyway. We definitely could.
3.56 mole.
It would still, that's definitely one way to do it. Okay? But we just need to get rid of this. And it says divided by PT. So I'm going to multiply both sides by PT. And then I got it. So I got the partial pressure of nitrogen is equal to the number of moles of nitrogen times the total pressure divided by the total number of moles. So that's my equation for this particular problem. And we're going to use this how many times? 3 times. Changing this guy and this guy out, right? To these other ones. So that's another reason I like to solve variables first. Now we're done with our algebra. Now all we have to do is calculate it 3 times. Good? All right. So let's plug this in. The total number of, or the number of moles, sorry, the number of pressure of nitrogen is equal to the number of moles of nitrogen, which is 2.78. times the total pressure is 0.987 ATM, divided by the total number of moles we calculated to be 3.56 moles. You following me? What cancels? Moles goes away. We're left with ATM. Good. That's the unit of pressure we need. We put those in and we get 0.77 ATM. We're a third done. But now to find the partial pressure of oxygen is going to be the number of moles of oxygen, 0.75. And these values are exactly the same. 0.987 ATM divided by 3.56 moles. And that gives us 0.21 ATM. Are you following me? So go ahead and do the last one. The partial pressure of argon goes on top. What goes on top?
Moles of argon times.
What's the moles of argon? How many?
0.03.
0.03. Does everybody understand this? Or are you lost somewhere?
Yeah, 0.3.
And this is still the total pressure, this is still the total number of moles, so that stays the same. And we get 0.008 ATM. Is there a way to check to see if we did this right?
I don't know, to see if they equal.
Yeah, they better equal to this, right? Or pretty darn close. We do this, we get 0.988. That's pretty darn close. Within a thousandth, right? Why is it not exactly? Because we rounded somewhere.
It is 0.0 ATM, the pressure of argon.
Of argon, uh-huh. So if you wanted, you can write your own equation, right?
Minus P4. This is separated or something?
So this is the same equation, just solved for the partial pressure, right? So if you're looking for that, you have a problem, then you can solve for that and you got it, right? So, your call. If you want to write that down, you can.
N is the number of total.
NT is the total number of moles.
So N is the number.
Questions?
One more example.
Another example? Okay. I don't have another one here, so let's look at our worksheet. Okay, so on the back side, section 4 is some more ideal gas problems. And there's one more example on section 5. You guys want to do it together, or do you want to try it on your own?
Section 5.
What?
Section 5, is that right?
Yeah.
I'm on page 5.
Try it on your own.
Section 5.
And yeah, so on the very back side, the bottom, yeah, right here, section V, 5.
Do you have any extra worksheets?
Yep. Anybody else need one?
Thank you.
So it is right. If you don't want it in that form, you can change it, I think. That's changed to fraction to decimal. So. And I don't know if that changed the whole, if you wanna change it back, you'd have to do that same thing, go like scientific.
So, we just said like this, one at a time. So we'll start with, so we'll say, total pressure was
see, with this total,
Then you have
put
to,
all of them the same equation,
then the only one that changes will be this.
Exactly.
So then for this one, it's gonna be 2.05, right?
Yes.
And these two are getting
But I can put in the same equation, each of them, and then I divide it by total number of moles. But for each of them, the numbers will differ.
Yeah.
Equation. That's the same.
That's it.
That's it.
Not too bad.
No, that's very easy.
How we feeling?
You're feeling too.
Okay? That's all I have for you today. Yeah, that's the answer for this one.
Is this going to be?
Yeah, this is in the video. This is today's. If you're not done, continue to work, and if you have more questions, we can go over more examples. Yeah.
Can we go over the second question in part 4?
Yeah. Second question in part 4. Any questions on this one first? Got it? Okay. So in part 4, the second question where it says determine the molar mass. Okay. Did you do part 1?
Yes.
Okay. And I don't know if they're together, but let's see.
Yeah, I wasn't sure if they were.
Which one?
Determine the molar mass of a gas if a 11.6 gram sample occupies 855 milliliters at 1.20 atm and a temperature of 18 degrees Celsius. Okay. So we got to determine the molar mass of this gas. What do we know? We know volume, we know pressure, and we know temperature. So from here, what can we calculate? Number of moles, yeah. So N is going to be PV over RT, right? Once we get the number of moles, we already have the grams. So how do you find molar mass? Grams per mole. So it's going to be 11.6 divided by the number of moles. Does that make sense? Yeah. Any other questions on anything? Okay, today's the last day for your exam, right?
It's not +6 because there are 2 alumina. It's still +3.
It still is +3, yep.
We're just 3.
But to figure out the other ones, we have to do
We have
that,
to
yep.
multiply by how many there are.
This is just to figure it out, which one, what the other ones
The
are.
oxidation number is positive.
Yep. Yeah.
In a typical example, like on the practice test, it had KCl plus APE,
Plus what?
AG,
Silver.
NO3 parentheses,
Yeah.
yields,
What's the number outside the parenthesis?
there is no one.
Then we don't need to write it, right? I mean, you can write it. It doesn't do anything. That's okay.
Yield KNO3 plus AgCl. The way I did it is I put K plus Cl minus,
Rounded early.
Say plus 1 and minus 1.
and then I put plus 1 and kept NO3 as -1 or -1.
Sure, it is, but we need to find what it is for nitrogen and for oxygen. But here's an easier thing to do. A little easier. Since nitrate doesn't change, can we just call it -1? Sure, we can, but only since it's the same on both sides. If there's a nitrate on one side and it's not a nitrate on the other side, we can't do that.
No, it's all the same.
So we could have done that up here too, right? You see how this didn't change? We could have just says, okay, the whole thing is -2 together. We could have. That might have been a little easier.
That's only if it's the same.
Same polyatomic ion on both sides. So if we do that, this is still +1, right? And this one is +1, and this is -1. This is not an oxidation reduction reaction. But what's the question?
Oh, my question was that if it's the same
I think the phone line is also
polyatomic ion, if we can just leave it as -1 instead of trying to find the,
Yes, you can.
only if it's the same. Because I
And
don't know.
a lot of times it is, but let me say on this, do we even have to figure out the oxidation numbers on this one? Why not? Because it's a double replacement reaction. Since it's a double replacement reaction, it will never be an oxidation reduction reaction. So we don't have to worry about oxidation numbers. But yeah, like on this one up here, I could have just says, okay, this is -2 here, and this is -2 here, right? See, we didn't use that one anyway. This one was oxidized, and this one was reduced. Did that help? Yeah.
That wouldn't affect, because you say they're the same in both sides.
Yes. Nope. Because why is? Let me write this again. Okay, now let's do it. If we say this is -2 and this is -2, right? And this is +3. Now let's do this. +3 times 2 is +6. -2 times +3 is -6. Does that equal 0? And it should. Right? And we come over here, this is +1. +1 times 2 is +2. There's only one of these, so that's -2. That's 0. Because we just said this is -2, because that's the charge of sulfate. So we could have done that, it would have saved a little bit of time. But the reason why I did it the other way is because sometimes, like on that practice problem you said, is calcium sulfate. If you just have one comment, you have to know how to find the oxidation number for each element. Good? Any other questions? No questions? Okay.
Which you have questions? This one was also on the practice.
Okay.
So, as we already talked about this, which of the following is
Okay.
So 150, yes.
Okay, which of the following energy diagrams represents a slow reaction?
Okay. So there's going to be one just like this on the test.
So that's.
Okay. So let's look at this. I'll draw all these. So we got from here to here. It goes like that, right?
I understood the slow reaction, but I guess the large negative free energy change.
And then we have one that's like this, and one that's like this.
Do you have like there's one more.
And one more. This. Okay, so what's the question?
Oh, I got it wrong. Oh, my question is, which one represents a slow reaction with a large negative free energy charge? What does it mean by a large negative free energy charge? I know
Negative delta G. Large negative delta G. That's what it's asking, right? So which one is fast or slow? What does it say?
Yeah, which one represents a slow reaction?
Okay, so for everybody, so we have these three graphs. We want to know which one is slow. So let's take out the fast ones. So if this is A, B, C, D, and E, which ones are fast?
E.
E is fast. What else?
The next one is
C and D. Do you all understand that? Yes or no? If you don't, I'll show you.
yes. That's easy.
Yep. Okay, remember that the speed is determined by the activation energy. So here's a small activation energy. Here's a small activation energy. And here's a small activation energy. You find the highest point and you just draw a straight line. And that activation energy is that little hump. So compared to these ones, whoops, that's a huge activation energy.
That's huge.
If it has a small activation energy, it's going to go fast. If it has a huge activation energy, it's going to go slow. So that means our options are A or B for this one, right? But now we have to find one that has a negative delta G. Well, what does negative delta G mean? Does it mean spontaneous or non-spontaneous? It means spontaneous. So which one will happen all by itself? Both of them. Okay. That was a bad question. So read that question again.
Which of the following diagrams represents a slow reaction with a large negative?
A large. Okay, a large. We got to have a large negative. So what is that? That's the difference here. This is delta G right here. Which one has a large one? B. Does that make sense? What?
You were gonna do it again, like one more time, like all the.
Yeah. I'll use a different color. So we want, first of all, let's find a slow one. So you see how this is a small activation energy on all three of these? Do you understand that part? So those are fast. Those aren't the ones. This has a large activation energy. So these are the slow ones. Good? And delta G is the difference between the initial energy and final energy. Initial energy, final energy. And remember, the energy is right here. So delta G is that part right there.
Or not, sorry.
You with me? This one has a larger negative delta G. This one's a smaller negative delta G. Good?
Yeah, because I got it wrong on the practice.
This one has
Yeah.
a larger than.
I went through it the second time too, still wrong.
Does it make sense?
When there's a slow, it's delta G is negative. When you have a larger, delta G
They're
is
answering the pressure, so that makes sense.
No. Nope. Delta G is negative when it looks like this. Delta G is positive when it looks like this. Yeah? Because delta G is final energy minus initial energy. The final is always, this is the time. So here's our final. Here's our initial. This is our final. This is our initial.
I got like 2 points.
So if we look at our final minus initial, this is a big value, so we can say that's 10. This is a small value, maybe that's 5. We end at 10 minus, we started at 5. That's going to be what? Positive 5. That's a positive delta G. This right here, if this is 10 and this is 1, for example, our final is 1, so we energy final minus energy initial is 1 minus 10. And that's negative 9. So that's a negative delta G. That tells us it's spontaneous. Yeah? What else?
negative 9 is spontaneous.
It's not that it's 9, it's that it's negative.
Negative is spontaneous. Positive.
And I just pick these numbers out of my head.
Yeah,
You
but
don't have to have numbers.
positive is not spontaneous.
That's right, non-spontaneous.
Do we have a kind of sheets to
A what?
sheets of like to see the negativity and stuff?
Electronic, yeah. Uh-huh.
Can I have
I hope I do. Yeah, I do. Do I? You ready for the test? Okay. Well, I can't be answering questions for other people, but wait just a minute.
oh, wait. Have a white paper.
A what? Blank paper? Yeah. Anything else from anybody? Yeah.
I don't want them to use the 6.022.
So 1 mole of anything is equal to 6.022 times 10 to the 23 atoms or molecules or ions, right? The particles. So if we're going, if they say how many hydrogen atoms and they give you how many grams or how many moles, then yeah, we use this. Use the mole roadmap. Do you have this right here? So you get this on the exam. So this tells you use Avogadro's number when you're going from moles to particles or particles to moles. And particles can be atoms, could be molecules, formula units, ions, but mostly molecules and atoms. Yeah.
I was just how would I know when to put it in the top or in the bottom?
See, this is moles. The mole roadmap says if we're going from moles to particles, well, we have moles here. Where is it? So we have moles, so we want moles down here. If we had atoms, we want atoms down here, then that means this goes down to the bottom. Because this is the number of particles. No? So 6.022 times 10 to the 23 is the number of particles. Moles is not particles. So we put moles down here so they cancel. But if we had so many molecules of this, and we want moles, then we put molecules down here so they cancel. And that's when we put the 6.022 times 10 to the 23 molecules down the
But
bottom.
since it's mole, I don't need to. Since it's mole.
Then it's moles, then one mole goes down here, molecules goes up here. You still have to use this number, it just goes on top now. Does that make sense?
Yes.
So use just dimensional analysis so that your units cancel out.
So when it says particles, atoms, or molecules.
Mm-hmm.
Mushkat says we can set till 3 o'clock.
Okay, you have, oh yeah, we're
He
gonna,
said we can set till 3 o'clock.
we good?
Yes.
Okay, so let's see. C4H10 plus O2 gives us CO2 plus.
No, you said we can stay until 3 o'clock to pass the exam. Ask
Nope.
them.
Cannot. All right. You ready? All right, so where should we start? Do you like to show your work?
We have to balance the equation.
Okay. No, do it, then do it. That's what you should do then. Okay. So what do you want to start with? Carbon, hydrogen, or oxygen?
Carbon.
Sure. There's 4 on this side, so what coefficient goes right there? 4. So we got 4 on both sides. Now let's do which one?
Hydro.
Hydrogen, there's 10 on this side, so what goes right there?
5.
Does that make sense in your mind? I'm asking her. So we got 10 on both sides. Now let's do oxygen. Which side should we count first? The ones on the left or the right side first? The right, because that's already balanced. So we got how many right here?
8.
8. Plus how many right here?
10. 5.
We have 5 right here. That's a total of 13. What number times 2 is 13?
Half number.
13 halves. Or 6.5. How do we get that number? 13 divided by 2 is going to give us 13 halves, right? Does that make sense? Then 13 halves times 2, that's 13. It's all balanced, but we can't keep it that way, can we? So we have to multiply everything by 2 to get rid of that denominator. So we got to multiply that by 2, that by 2, that by 2, and that by 2. And it's still balanced because we multiplied a balanced equation by the same number all the way through. So you don't have to use fractions. You want me to show you a way without doing fractions?
And the great thing is the only number that we're actually changing is the first one, because this is the partial number of the line.
Maybe I can set what her on the exam so already.
All right.
She needs help.
All right, so let's do this without fractions.
Fractions, exactly. Teacher, I think this question is a lot because you are focusing more in this.
That's the partial pressure, which is coming from 1 to 2.
We you have these more, that's why you're focusing.
Because she had a question. All right, so here we go.
But now we
We're
don't
gonna do the
have
same thing with carbon hydrogen. There's gonna be 4 right here and 5 right here. So that part doesn't change. Now, we see this, we have 13 on this side, and this side's always going to be even. So let's make this side always even. See this right here, that's even because of this 2 right here. There's only 1 right there times 1, that's odd. So let's multiply this by 10. Or sorry, not by 10, by 2 to make it even. Does that make sense? Multiply it by 2. Okay, that's going to be an even number. And if we do that, we have to multiply this side by 2 because we just changed the hydrogens, right? Now we just changed the carbon, so we have to multiply this side by 2. Do you get that? Then when we add this, we get 16 plus 10, that's 26. What times 2 is 26? And we get the exact same thing. So, your call, your choice. If you don't want to deal with fractions, that's the way you'd go about it.
2.7.
If we can leave fraction, it doesn't
So
matter.
now.
You can't leave it that
The
way.
way to check this is now just add all the partial pressures together and they should equal
Okay.
the total pressure, which you can.
What else?
I think that's all.
Es todo?
I'm ready for your.
That's
Thank you.
Yeah.
partial pressure right there. Cool. Nice. That is actually something I can say.
Okay, are you ready?
Would love to have fun teaching. But anything specific? We'll, back in the fall, I wanted to teach philosophy. So it's just so interesting. But I really still like biology. So.
Still have questions?
I just need to look the.
Biology.
Okay.
Philosophy.